Let's look at some more questions, and these are examples where things are badly behaved. Okay, so let's look at R over Q. Here I mean Q pinched as a single point. Okay, so let's call that X as the quotient. So this claim is that this is not Hausdorff. Same is true, it's even worse if we take the quotient group, but let's take this. Namely, if I have R and I take two different points, X and Y, let's just say they are irrational numbers. So Q, remember, becomes a single point. Otherwise, if they are different from, I don't mean the quotient, I take two irrational points here, R minus Q and also this and R minus Q. And I take an open set, its inverse image must be open. Okay, so this is because if I take an open set, namely if X comma Y belong to R minus Q and X is not Y, or let pick these points, I could pick specific ones, but let's take any two. If U, V, so U bar, V bar contained in X are neighborhoods, then their inverse images. So Q inverse of U bar equals U and Q inverse of V bar equals V are open in R. But what does that mean? So they have open neighborhoods, and in R they can be disjoint, they can be pretty small, all that happens. But the class of Q, but let me put it this way, Q intersection U is non-empty and Q intersection V is non-empty. Therefore, class of Q, which is going to be a single point, remember, belongs to U bar and V bar. So U bar intersection V bar is not empty. So generally speaking, quotients can be really badly behaved, and well, not this but the other R over Q, where we're looking at two things equivalent. If there are differences in Q, you have the similar phenomenon happening. One tries to deal with them in a different way using non-commutative spaces. There are various ways of trying to avoid these, but simply naively taking the quotient is generally not a good idea. But our second example is where it is surprisingly somewhat a good idea, even though the quotient is badly behaved. So let me just write it here. So let's look at two lines, and then I make some identifications on them. So I'll look at R cross 0, 1 for definiteness and divide it by equivalence relation, where tilde is generated by y comma 0 is equivalent to y comma 1 if y is less than 0. So only the negative numbers, so we start with two lines, and then here is 0 and here is 0, and we identify these sides. What that gives you is a space which looks roughly like this. I have a common part which I might as well draw as a line, and then it branches off into a sort of pink line that goes above, so a purple line that goes above, and maybe an orange one that goes below. Kind of a picture like this. But the picture is a little bit different than what you see. Let's see this point here. So the thing, crucially, it's a less than. So if I look at strict inequality here, so if I look at the point 0 comma 1 and 0 comma 0, these are different points. Okay, so this is non-Hausdorff. Non-Hausdorff. Well, most of it is Hausdorff. It's only these 2 points cannot be separated. Any neighborhood of so here is 0, 0, I can draw 0, 1, 0, 0, strictly speaking its equivalence class intersects any neighborhood of 0, 1. But what are these neighborhoods? They are things whose inverse image is open. So they do include some rather nice neighborhoods. Namely, if I look at the image of this open set, so images of open sets and quotients need not be open, because if I take the image and then take the inverse image, I can end up with more than I started with. But if I took this image, open set, the blue one here, then its image here would be up this and this guy above, and will not go to the lower part at all, and its inverse image will be back to this. Okay, so the thing is that there is an interval. So even though what is clear is that if I take any interval here and an interval here, they both will include, and I take a typical image neighborhood of this guy, which is gray, it will give me a gray region which includes this and this. So first of all, the pathology here is the non-Hausdorffness, which is that if I take any open set containing 0, 0, it will involve an interval like this, and it will contain an interval like this, and 0, 1 will contain an interval above, and they both will overlap at points which are close to the origin, so they intersect. They are not Hausdorff. But remarkably enough, every point has a neighborhood homeomorphic to an open interval. So just like with real numbers or circles, okay, and you would think these are two connected examples where this property is true, that every point has an open neighborhood which is homeomorphic to an interval. The same is true for a circle. Of course, for disconnected spaces it's true, but provided it's true for each component, so we may as well stick to connected spaces. So this is a connected space. It has the property that each point locally looks like an interval. It has a neighborhood that looks like an interval. So locally in that precise sense. However, it's non-Hausdorff. So locally having an interval as a neighborhood is called a one manifold. These are one-dimensional spaces. Curiously enough, you have one manifolds which are non-Hausdorff, which are different from these. But indeed they can be classified. And this turns out to be rather useful in a particular theory, which we will not see, but the next example we will see is just an important example in this, or rather the key ingredient of a crucial, very important example in this. And we'll just, this example 3 will be more or less drawn as a picture. It's important in geometric topology. This is just for culture. So let's look at R2 by tilde, where P is equivalent to Q if they are in the same leaf, and I'll draw the leaves. And what are the leaves? Most of them are fairly straightforward. There are certain leaves on the left which are going to be just vertical lines. Let's make it even more vertical. And these go all the way. Obviously, I'm not drawing all of them. Let's make it straighter though. And here also there are a bunch of vertical lines. These go all the way, even in terms of height as well as sideways. Okay, somewhat untidy picture. But what about in the middle? In the middle you instead have, I would like to say parabolas, but they are asymptotic to the infinity. So you can take graphs of functions. So we can write these equations very precisely. Okay, so you have these gray functions. Okay, so any one of them, let's say a favorite one, is the graph of, well, as you go to 1 or minus 1, you have to have it getting sharper and sharper, 1 over 1 minus x squared, let's say. And so suppose this is minus 1 and this is 1. So over here, this graph is y is 1 over 1 minus x squared. And in general, you have graphs being y equals 1 minus y equals 1 over 1 minus x squared plus c. So indeed we can write these two formula, that is, let me write x1 y1 is equivalent to x2 y2 if and only if one of the following happens. So this C is a right vertical push upwards, and these are all graphs. These are mutually exclusive conditions, so exactly one of them happening, or at least one is the same thing. So first of all, we can be up to -1. X1 is less than or equal to -1, or x1 is greater than or equal to 1, and and they're at the same level, and x1 is x2. So x1 and x2 are both here. So we are identifying 2 points which differ only by y, provided they're here. And over here we want to say that the c's are the same. So that is saying that y1 minus so second condition is only valid if the first one is true. So x1 belongs to strictly -1 1, and the next part is well defined only if this is true, but we assume so x1 and x2 both belong to -1 1, and y1 minus 1 over 1 minus x1 squared, which is the c of this graph, is y2 minus 1 over 1 minus x2 squared. Okay, so we have defined an equivalence relation. It's easy to see it's an equivalence relation. It's not just generated by this. It is actually, well, we have to take reflexive closure and symmetric closure. So is that, but perhaps it's automatically true. Yeah, every point is equivalent to itself in all of these cases, and the conditions are also symmetric and transitive. So this is the equivalence relation. So, well, what happens in this case? So the quotient is actually the same as example 2. Yeah, so what are our two lines? So our example 2 had a pair of lines, and then let's color them. So we had a purple line and an orange line, and we had some special red points on them which sat one above the other, and everything on this side was identified with everything on this side. Okay, so with a slightly upside down picture, you can see that if I took a purple line which started here and went off this way, and an orange line which started here and went off this way, then we will actually get points in the purple line identified with corresponding points in the orange line up to and including, but not including this end line. So our red points become the points where this guy is here and this guy is here. So you just formally draw these two curves, meaning make sure they're asymptotic and they're asymptotically zero, coming from opposite sides. You can see that there is, these red points are not identified with each other. Nothing beyond them is identified, but these parts are pairwise identified, so we get the same quotient. So this picture is what is called a foliation. It's, you see, and any piece of it is a nice division into vertical lines very smoothly wherever you are. Everything is nicely divided into lines. Okay, so it's divided into lines, and this kind of quotient where we are, so leaves are these lines into which it's divided, and these quotients are always going to be one house in this kind of foliation. I won't be precise what it is. Are going to be these one manifolds. In nice cases, real numbers or circle, but in these kinds of cases, non-Hausdorff one manifolds. So this is a case where your quotient is bad in a sense, it's non-Hausdorff, but is nevertheless actually very useful. Okay, so this would be our final example of quotients that are relevant in geometric topology.